In this video we are going to have further discussions on topological equivalence of topological spaces and on topological properties. We know that when the function f, which is defined from the topological space x to y, is a homeomorphism, then its inverse function, that is f inverse, its inverse function f inverse must be continuous. But you know, it's actually equivalent to, and the continuity of f inverse, continuity of the function f inverse is actually equivalent to the statement that for any open set O in X, F0 is open in Y. That is, it's equivalent to the fact that F is an open mapping. So if F is an open mapping, if F is an open mapping F, where F is defined from X to Y, if F is an open mapping, then if its inverse function actually exists, moreover, if its inverse function exists, then F inverse is a continuous function. Or in other words, if f inverse for a function which exists from x to y, if f inverse is a continuous function, then the function f will be an open mapping. Therefore, we can restate the condition for a function f which is defined from x to y to be a homeomorphism, and that statement is, or the condition can be restated, and that statement is if f must be 1 to 1, f must be 1 to, then f is continuous and f is an open mapping. So these are the four statements or conditions required. The first condition is if f must be 1 to 1. Second condition, so first three conditions are same. F must be 1 to 1, f must be 1 to, then f must be continuous, and finally f must, it is not about f inverse. If you are using f inverse, then f inverse must be continuous. You have to say it like f inverse must be continuous, but instead of using f, you can use f inverse, you can use f, the function f. When you are using the function f, then you can state that f must be an open mapping. So that's all. Next, we are going to see another definition. See the definition. It's about the topological property. The definition gives us a clear idea about the topological property, or how we could define and the concept of topological property, or the concept of topological invariant. A property P of a topological space is a topological property. See, it's about, this definition is about the property of a topological space. A property P, we call that property P of a topological space, is a topological property, or it can be called a topological, the property, we can say that the space is topologically invariant in such situation, but we are coming to that point. But see, here first let us see what is topological property. The property is called a topological property if the space X possesses the property. Whenever the space X possesses the property, then if Y is another space, suppose Y is another space which is topologically equivalent to X. See what is the definition of a topological equivalence. We have already seen the definition of topological equivalence. So X is the first space which is given, and that space is having that property P. P is the property of the first space X. It is also given that the second space, what's the second space? Y is the second space. The second space Y, it is topologically equivalent to X. That means there is a homeomorphism from X to Y. When Y is topologically equivalent to X, if there exists a homeomorphism from X to Y, And when there exists an homeomorphism from X to Y, it's topologically equivalent. So provided that it is topologically equivalent, then the property will then be transferred to the space, the second space, or whenever y is topologically equivalent to the topological space X. If there is a property P which exists in the space X, then that property will be possessed by the second space also. Only such properties are called topological properties. So if P can be called a topological property, if P is the property of X and Y is homeomorphically is topologically equivalent to X, or if there exists a homeomorphism from X to Y, then Y must also possess that property. So that is the definition of topological properties. And we say that the property is topologically invariant. There are some properties which are topologically invariant. There are some other properties which are not topologically invariant. What's mean by what's mean by topological invariance? Topological invariance. A property is said to be topologically invariant. A particular property is called topologically invariant whenever two spaces are topologically equivalent. That property, the property possessed by the first space, if that property is possessed by the first space, then that will be possessed by the second space, and vice versa. If the property, if a property is topologically invariant property, see, then both spaces will have that property. If one of the spaces has the property, then the other space will definitely have that property. So such properties are called topologically invariant properties. Okay, next we are going to see in a theorem, we will state that one property is topological invariant. So this is an example for a topologically invariant property. That property is separability. See, what is mean by separability? You have learned that property of separability, or otherwise you should see what is separability. Separability is a property of a topological space. Definitely we will explain this property here in the explanation or in the expansion of the proof of the statement. So then you can see it there. And the statement of the result is that separability is a topological property, and that means if X is a topological space having the property separability, or if X is separable, if X is a separable topological space, and Y is topologically equivalent to X, or Y is homeomorphic to X. If Y is homeomorphic to X, then Y is also separable. Okay, how can we prove this? Let's go through the steps of the proof. So it is given that let X be a separable space. So here we begin with the supposition that we suppose that X is a space. X is the given space, and that is separable also. So let X be a separable space. Then when X is separable, see, if the space X is separable, when can we say that the space X is separable? That you have to state now. If X is separable, then there must exist a countable dense subset. In this, that space must contain a countable dense subset such that that subset can be called A, such that there must exist a countable dense subset, and that means closure of A. Closure of A must be equal to such that closure of A is equal to X. See, a closure must be equal to X. So let X be a separable space with the countable dense subset. Countable dense subset A, and A is the countable dense subset. That is the name we choose for that countable dense subset. And also suppose that Y is a space which is homeomorphic to X. The second space is given here, and that space is Y. It is homeomorphic to X. So now we are set to proceed the remaining part of the proof. Since it is given that Y is homeomorphic to X, there must exist a homeomorphism. there must exist a function having the 4 properties. So then there must exist a homeomorphism. Yes, that homeomorphism, let's choose that homeomorphism f. Let f be the homeomorphism that exists from x to y. And this homeomorphism has the 4 properties. Properties are it is 1 to 1, it's then on to, and f is continuous, and f is open also, or f inverse is continuous. F is continuous and f inverse is also continuous. Okay, these are the 4 properties. And then see, we know that then you can see that f of a, what is f of a? F of a is the image of the subset of x under the function f. Using the function f, when the function f is applied, then you get the image of a. A is the subset of x. Where do we get that image? We get that image as a subset of the second space. We have, that is fa is a subset of y. So we shall and we shall now prove that we are proceeding to prove that this subset fa is a countable dense subset of y. Actually, what do we want? We want to show that y is also separable. So x is separable, it is given. See, x is separable is given, and we want to show that y is also separable. Okay, if we can show that y is separable, then we can say that separability is a topological property, because y is topologically equivalent to x. There is a homeomorphism from x to y. Okay, and then whenever the space x has the property separability, if it is transferred to, if it can be transferred to, if that property can be transferred to the homeomorphic image space, that is y, then you are done. So for obtaining that, the only way is to find a countable dense subset of y. See, we want a countable dense subset of y. Actually, we are looking for a countable dense subset of the second space, and actually and a candidate, and there is a candidate for that countable dense subset. There is a possibility that fi is a fa is the image of the countable dense subset of x. That is a is the countable dense subset of subset in x, and then its image is taken fa. So there is a possibility that that image, that is f of a can be a countable dense subset of y. So we are now proceeding to verify this, whether f of a is a countable dense subset of y. Since f is 1 to 1 and on to, since f is 1 to 1 and on to, the number of elements present in A must be equal to the number of elements in A equal to the number of elements in f of A, due to the reason that f is the function f is 1 to 1 and on to. Yes, since it is since f is 1 to 1 and on to, you can see this. It is very easy. So number of elements of A must be equal to number of elements in f of A, because each element in A is mapped to exactly one element in f of A, or exactly one element in the second space. So this relationship is the relationship or the correspondence is 1 to 1. So for each element in A, you have you have exactly one element, exactly one image in y, and that is present in fa also. Therefore, and this statement is true, and therefore f of a is countable. Since why f of a is countable? Since a is countable, we know that a is countable. A is a countable dense subset of x. The statement says that a is countable. So f of a is also countable. Next it remains to prove that closure of fa equal to y. If we can show that, and in addition to this, in addition to the fact that f of a is countable, if we can also show if we can show that closure of fa equal to y, when we take the closure of fa, and that becomes the whole second space y, then we are done. For that, see, let us choose. How can we do this? For that, you have to choose an open set, an arbitrary open set from the second space y. So let O be a non-empty open subset of Y. We choose a non-empty open subset. Arbitrarily we choose a non-empty open subset of Y, and we name it O. Let O be, and let O be a non-empty open subset of Y. Then F inverse of O. See, F inverse of O is a non-empty open subset in X. Why? It's because F inverse is continuous, or see, F is, since it's because F is continuous. F is continuous. We know that F is continuous, and due to that reason, whenever we choose an open subset of Y, then its inverse image, that is F inverse of O, must be open in X. Okay, and therefore, since F inverse of O is an open subset in X, and also closure of A equal to X. So I have stated that closure of A equal to X already. So I have told you that since closure of A equal to X, it's because X is dense. A is a dense subset of a countable dense subset of X. So closure of A equal to X, and therefore F inverse of O contains some member of some member of A, and that member can be named A. So F inverse of O must contain some member of the set A, and we name that member A. So small a of it must contain some member small a of A. Now we can think about the image of that element, image of that member, and the image of the member is F of A. F of A, it must be a member of F of capital A, right? So it must be a member of F of capital A. Thus O contains, see, and also see F of A. So A, thus O contains a member. See, thus O contains a member. See, therefore, O contains a member. When you take the image of the element A is a member of A. See, A is a member of A, and also when A is a member of A, F of A must be a member of F of capital A. That's true, F of capital A, and also since A is a member of F inverse of O. Since A is a member of F inverse of O, FA must be present in O also, because when we get O, the open set O, by applying F on F inverse of O, by taking F of F inverse of O, we get O. You can apply F on F inverse of O, and this is open. So F of F inverse of O will also be open. Anyway, O is open. No further explanation is required, because O is taken as an open set, open subset of Y. So no need to further show that O is open. So it's O is open as we have taken it. Then O is open. So thus O contains, that set O contains the member F of A. O contains the member F of A, and we also get that F of A is contained in F of capital A. So every non-empty open set in Y. See, therefore every non-empty open set in Y contains at least one member of FA. Thus, see, how do we get that? See, we get that FA is a member of F of capital A. Also, FA is a member of O. Thus, every non-empty open set in Y. Which one is the non-empty open set in Y? O is the non-empty open set in Y that we have chosen in the beginning. O is the non-empty open subset in Y, and that O contains the element FA. The simultaneously FA is contained in F of A, and therefore we can say that F of A, F of capital A, is a countable dense subset of the second space Y. Thus we so you can write, you can express it mathematically writing F of closure of A. Thus we get F of closure of A equal to Y. The reason is explained. Actually, the reason for writing that is given here. See, thus O contains a member f of a. At the same time, f of a is a member of f of capital A. And so every non-empty subset of every non-empty open subset of Y contains at least one member of FA, and that means FA is already we have proved that FA is a countable subset. Now it is dense also. In this line it is clear that FA is dense also. Thus you can write f of closure of f of a equal to Y, and hence Y is the space Y is separable. So okay, that's all. Thank you.